Let's now provide an algorithm that finds a matching in a given bipartite graph. So now, just as before, we construct a matrix which is close to adjacency matrix, but now instead of having a symbolic variables here, and instead of having just random weights here, we'll have a specific random weights. So in case our vertices ui and vj in different parts of the bipartite graph are adjacent, we'll put a value in the matrix which is 2 to the power of wij, where wij is taken at random from the set from 1 through m. And now let's first compute the determinant of this matrix, which we'll denote by A. This determinant is equal to sum of the signs of permutation over all permutation multiplied by the product of the elements on the transversal. But whenever we have a non-zero term here in the sum, this term would be equal to a product of powers of 2, like this. And this would be equal to the 2, and this would be equal to 2 to the power of sum of wij's if our permutation P corresponds to a matching, and I will just write P is a matching, and 0 otherwise, because then we'll just have a 0 value creeping into the product. But now we see that here at the power of 2 we have just the weight of the matching as the sum of the weights of the edges. So we see then that our determinant is just sum over all matchings of our graph, sum over all H, which is a matching in G, and here we have plus or minus 2 to the power weights of this matching. And now let's H mean be the matching with the minimal weight. And let's take out of this sum the power of 2, which is minimal. So W of H mean. And in this sum, we'll now have summation of plus or minus 2 to the power W of H minus W of H mean over all matchings H. And what we can see now, with high probability, which is given to us by an isolating lemma, our graph would have a unique matching of a minimal weight. And then here, in all of the summons, but just one, we'll have strictly positive numbers, so that the weight of all the matching, but the H mean itself, they would be strictly higher. And exactly one term in our sum would be equal to plus or minus 2 to the power of 0. So we actually have the sum of several powers of 2, exactly one of which is the 0th power of 2. And such sum is an odd number. And an odd number cannot be 0. So with high probability, this guy is an odd number, and in particular it's non-zero as well. And this is exactly what's of use for us. So already, by computing the numeric value of determinant of our matrix, with high probability, we can find the weight of the minimal perfect matching, assuming that it's unique. This weight would be the maximal power of 2 that divides our determinant, because our determinant is equal to this power of 2 multiplied by some odd number. So now we can extract this W of H mean as the maximal k, such that 2 to the power of k divides the determinant. And next, as soon as we are able to extract this minimal weight of the perfect matching, we now can guess what edges participate in this perfect matching. Without regenerating any numbers in our matrix, which we have here, we'll perform the following. Assume that we have many processors available. So now, in parallel, we can assign each processor a separate task like this. Take every edge of the form ui vj, remove both of endpoints of this edge, and by using the very same technique, find the weight of the minimal weight perfect matching in a graph G minus ui vj. And for every ui and vj, this is done in parallel. So we can do this just by virtually striking out the ith row and the jth column, and considering what is called a joint of this element, the ith element, the determinant of the matrix without this row and column. So let's denote the corresponding minimal weight of the matching in this graph by W of H min ij, if we know that this edge ui vj participated in a unique minimal weight perfect matching in G, then to get a minimal weight perfect matching in this graph, all we need is just to take the minimal weight perfect matching in G and remove the edge from ui to vj. So the weight of hij min would be equal to W of H min minus wij if ui vj was in H min. And can the matching in this graph has a smaller weight than this? No, because if we were able to find a matching of weight smaller than this in this graph, we would immediately augment this matching with an edge from ui to vj and get a matching of weight smaller than this one, which would contradict the choice of H min. So we actually have the following dichotomy, that this guy is equal to exactly this difference in one case and is greater than the same difference in case ui vj is not in H min. So now the presence of this edge from ui to vj in the matching can be guessed by, again, computing a determinant for a matrix of dimension 1 smaller than A and performing simple arithmetic comparison. So now, how do we implement this algorithm on a parallel computer so that we benefit from the ability of carrying out all these operations simultaneously? Here, a good idea would be the following. So we'll assume that we have a processor available for every edge of our graph, or moreover, for every pair of the vertices, one of them from the upper part and the other from the lower part. So we have these processors for every pair I and j. Then we supply these processors simultaneously with binary inputs. So we supply the processor with 0 if there is no edge between the vertices in our graph, and with 1 otherwise. So thus we have a parallel input here. Then each of the processors fills in the cell of the matrix, and the matrix is stored in a shared memory, but each processor fills in a single cell with this 2 to the power of randomly generated wij. And now by this time we have in a shared memory a matrix stored. Now we compute the determinant of the matrix, and this step can be done in polylogarithmic time for parallel computer. And then again, after we compute the determinant and we now know the weight of the minimal perfect matching, each processor again starts doing its own work. So each processor ij computes the determinant of submatrix of the adjoint and checks for this property. So again, we have a computation of determinants, but now all these determinants are computed in parallel. And by the end of the computation, which again takes polylogarithmic time, each processor knows whether it should output its edge. So the output is a simultaneously produced Boolean vector, which is an indicator vector of a matching. So we have this parallel scheme where the input is a characteristic vector of the graph itself, of the edge set of the graph, and the output is the characteristic vector of a matching in this graph. So the last thing that we can comment on here is how we estimate the probability of a failure. And the failure here can be due to that we have more than one minimal weight perfect matching. And this probability, according to isolating lemma, can be bounded above by 1 minus m minus 1 over m to the power of cardinality of E, and cardinality of E can be bounded by n squared. So now this can be bounded by 1 minus 1 minus n squared over m, which is n squared over m. So we can see that to make the probability of failure really small, we need m to be sufficiently larger than n squared, which is quite reasonable.